Hello everyone and welcome. In this tutorial, we're gonna solve the first example of a dynamic programming problem using SESV. Our problem today is climbing stairs. Climbing stairs fall into a few choices category that we have learned before. In our particular problem, it's gonna be 2 choices, and we're gonna do 7 examples of dynamic programming problems, and you will see how easy it is to solve these problems and any dynamic programming problem with SESV. Now make sure that you have learned about the modern law of dynamic programming, part 1 and 2, or SESV in short, part 1 and 2, before you continue. This tutorial is a part of the Data Structures and Algorithms class. First, let's try to understand our problem. Our problem is climbing stairs. We have n stairs, like what we have here, 1, 2, 3, with n equal to 3. At any position of the stair, we are allowed to take 1 or 2 steps. So if we are at 3, we can take 1 step to 2, or we can take 2 steps to 1. The question is, what is the total ways to reach the top? Or if we're from the top, what is the total ways to reach the bottom? That is our problem. In our particular setup here, where n equal to 3, we have 3 stairs, 1, 2, 3. The total way to reach the top is 3. They are these 3 lines that we see here. The red line, the blue line, and the black line. We already know this problem is a DP problem because it's in our DP series. But when you face a new problem, never forget to check if it is a multi-stage decision-making process problem. If it is, then we can use SESV to solve it. So climbing stairs, is it a multi-stage decision-making process? And the answer is yes. Making a series of decisions to change the system state will lead to desired final stages. For example, if we are at 3, we can keep making the decision of taking 1 step. So we're gonna go from 3 to 2, 2 to 1, and 1 to 0. And that series of decisions to change the system state, where we're at 3 and finally we're at 0, which is the ground, also our desired final state. So making a series of decisions of taking only 1 step at a time, that's gonna lead us to the desired state. Now remember, the final states can be the state that we desired, or can be the state where we cannot go anywhere further. We have no choices. So the answer is yes. It is a multi-stage decision-making process. Then we can use SESV to solve this problem systematically. Next, solving DP problem with SESV. Step 1, we're gonna solve the problem with pen and paper, just by hand. Then we're gonna code our deficit state tree. A quick reminder of SESV step 1. How do we solve DP problem with pen and paper by hand? It is simple, just by running its course. We do 3 steps here. First, we're gonna choose very small input size. In our particular problem here, I have purposely choose the size of the stairs as 3, and that's gonna help my deficit stage tree size very manageable. And it's important because in real-life interviews, you want to spend more time on solving the problem rather than managing an oversized deficit stage tree. Second step, from initial state, we're gonna make all possible choices to reach all possible final states. So when we are here at the initial state, we have 2 choices. The first one is we're gonna take 1 step, and the second one is we can take 2 steps. So if we take 1 step from 3, we're gonna end up at 2. So here we have 2. And if we take 2 steps from 3, we're gonna end up at 1. So that 1 here. Now from 2 and 1, we keep making all possible choices to reach all possible final states. So from 2, I can take 1 step or 2 steps. With 1 step, it's gonna bring me to 1, which is 1 here. With 2 steps, it's gonna bring me to 0, which is 0 here. Notice that 0 is the ground, and this is one of our desired states. So we're gonna stop here. But from 1, we're gonna keep making choices of 1 step and 2 step. And if we're here, we're making 1 step, they're gonna give us to 0, which is again our desired state. If we make 2 steps from 1, it's gonna be underground, which is -1. And that's where we're gonna stop. Now we're gonna continue with this branch. We're gonna make all possible choices to reach all possible final states. So 1 step and 2 step. If we take 1 step, it's gonna lead us to 0, which is our desired final state. If we take 2 steps from 1, it's gonna lead us to -1, which is underground. And that is also a final state. So by now, we have made all possible choices to reach all possible final states. And if we are step number 3, these are the comprehensive all possible ways that we can go from 3 to 0, which is from stair 3 to the ground. And for that, we have 3 ways to do so. The first way is making 1 step, making 1 step, and making 1 step. That's gonna lead us to here. The second way is making 1 step and then making 2 steps. That's gonna lead us to the ground. The third way is making 2 steps and making 1 step. It's also gonna lead us to the ground. So by what we're seeing here, the total way is 3. And that is what we have here. With this 3, we just finished step 3. Once we have all possible scenarios listed, we extract the information that asked by the problem statement. What we just have done is solving a dynamic programming problem by pen and paper. Next, we're going to turn the entire solution into code, and the computer then can apply the solution with much larger data set. For example, it can handle 1,000 stairs or 1,000,000 stairs. So now, we're gonna turn our deficit state tree into code. Or in the other words, we're gonna write some code that's gonna help us to create this deficit state tree pattern, the pattern that solves our problem. First, we create a function that called climb stairs. This is gonna be a wrapper function. Next, always name your recursive function depth first search, just to emphasize the importance of depth first search in our solution. Our depth first search recursive call always take in the state parameters, and for our case here, the parameter to identify the current state of the system is simply just the stair that we are at. So our recursive call is gonna take in the state parameter, which is the number of the current stair that we're at right now. Next, we have 2 choices at any given state. So we're gonna have 2 depth first search calls. The first one for the first choice, and the second one for the second choice. We have 2 choices, so 2 depth first search recursive calls. Now changing states. When we are at 3, if we make 1 step for the first choice, then the input of this depth first search is gonna be n-1. That's where we take 1 step. If we take 2 step choice for the second depth first search call, that's gonna be n-2, and the choice is 2 steps. Next, final states. If we reach 0, that's gonna be our desired final state, and we're gonna stop there. So what we're gonna have is, if n equal to 0, we're gonna stop branching. The second kind of final states is where we go underground. So when n is smaller than 0, we're gonna stop branching too. Now basically we're just transferring all of this into depth first search recursive function. We're gonna print out the stairs, which is a node that we have here on this console, to make sure that our depth first search recursive call is gonna produce this tree correctly. Finally, we call the depth first search function here. Now we can test our function. by running our solution and compare the printouts with the pattern that we see on the tree. So if we do a depth first search node collection for this tree, the printout should be 3, 2, 1, 0, which is what we have here, then -1, which is what we have here, then 0, which is what we have here, then 1, 0, which is what we have here, and then -1, which is what we have here. So by verifying the printout with a depth first search node collection on our solution tree, now we are sure that our code right here is representing our solution and it's correct. So what we have done in step 1 is that we have solved the problem with pen and paper, and the depth first search state tree represents our solution, and then we code the depth first search state tree. We also checked if our code is correct by comparing the depth first search state tree node output with the output of the code. To recap, always draw a full depth first search tree for 3 levels only. That is ideal. For our code, the number of choices equal to the number of depth first search recursive call. And in our code, we use the base cases, the final states condition, to stop the branching and to test if our code is representing our depth first search state tree solution correctly. We compare the code node output order, which is what we have here, with the tree visualization, which is a depth first search node collection pattern of what we have on the tree, to make sure the tree and the code are representing the same solution. Next, SESV step 2. We're going to calculate the information asked by the problem statement bottom up. This should be very straightforward after we have the tree. So when we look at our tree, whenever we hit 0, that is one way. If we hit non-zero, that is not a way. So basically we just sum up all the ways that we can reach 0. So in order to do that, in our code, if n equals to 0, we're going to return 1, which is here. If n does not equal to 0, we're going to return 0. And we can just simply return the sum of both ways. And that's what we have here and here. And if we run this, our result is 3, which is correct with our hand-solved solution. Now with our solution here, our time complexity is very high. We have 2 choices, and the tree is going to go n level deep. So the time complexity is 2 to the power of n, which is very bad. That's why we're going to do catching to make this solution performant. Next, SESV step 3. We're going to catch distinct depth first search calls. If we look at our tree here, we're going to see a lot of repeating depth first search calls with the same parameter. For example, here in this subtree, we're going to call depth first search 1 here at this node, and it's going to return 1. On the other part of the tree, like here, we can see that the same subtree is being called again, which is depth first search of 1. Now if we see this happen, we can just catch depth first search 1 here, and when we see it being called again, we can just look at the catch and return the result. And that's what we're going to do. We catch distinct depth first search calls. First, we're going to introduce our catch, which is basically just a map. And we're going to use n is our key because we only have one parameter here. So if we run our function and we see if there's something in the catch, we're going to return it. Otherwise, we're going to run our depth first search call as normal. Then we put the result into the catch, and then we return the result. If we run our function again, nothing has changed, and our result is 3. It stayed the same, but the time complexity of this solution has been improved to O of n with our catch, where n is the number of the stairs. To visualize the performance of the catch a little bit, we're going to have a look at a solution without the catch and a solution with the catch, with the number of the stairs of 40. So I'm going to uncomment this code. And we can see that climbing stair without the catch, it takes 4.6 seconds. And climbing stair with the catch, it only takes 0.12 milliseconds. So with the catch, the time complexity of our solution is greatly improved. We can also test our solution with Leetcode test cases. This is a screenshot of the result, and our result got accepted. Our quick summary. The characteristic of problem that can be solved by SESV. It is obviously dynamic programming problems. which is the multi-stage decision-making processes. The input characteristics, it can be any, it can be array, string, or graph. And our go-to solution to solve these kind of problem is SAMSDP. And the time complexity of the solution will always be the number of states created. If you find this tutorial useful, profoundly useful, then make sure to follow SESV tutorial, like, share, and subscribe to our channel, because dynamic programming is a mysterious subject with a lot of software engineers and algorithm learners. Until now, we have a solid way to solve DP problems. So if this is useful to you, let's help the world to demystify DP with SAMSDP by like, shares, and subscribe to our channel. It's gonna make YouTube algorithm to spread the video much faster. I also love to hear your story and how this course can help you to learn dynamic programming in particular or become a software engineer. So come say hi on LinkedIn. That is all for today's tutorial. Thank you for watching, and I will see you in the next video.